Welcome all of you for this. All of you for this. All of you for- Welcome all of you for this live session. This week 7 live session for NPTEL Smart Grid Basics to Advanced Technologies course. And my name is Gagan Meena, and I'm one of the TAs for these live sessions. And I'm fourth year PhD student in the electrical engineering department at IIT Bombay in power electronics and power system specialization. Let us begin with today's session. We will start with the overview of week 7 and then we will discuss certain questions. Just to remind you that the deadline for assignment 7 is March 12th, which is day after tomorrow, and deadline for the assignment 8th is March 19th. So please submit the assignments on time. And this is a link for where you can access all the recordings of the live sessions as well as the material which has been used for these live sessions. You can find the Google Drive link for that on the problem solving session tabs on the web page. And okay, so let us start with the overview. In this week, the main topic was the hierarchical control of three types of microgrid. We have already seen what is a microgrid. And here we discuss three types of microgrid. First, DC microgrid. Then first was AC. Then DC microgrid. And then AC-DC hybrid microgrid. These are the three. This was the main content of this week. We'll start with the microgrid control first. What are the key control variables which we are required to control in the microgrid, and or even in the normal our grid, the main grid also, whether it's main grid or microgrid, we are supposed to control these four elements, especially in AC grids, because frequency is not present in DC grid, neither the reactive power nor frequency. So in DC grid, we are concerned with voltage and active power. While in AC grid, we need to focus on all these four aspects. We need to control each of these four elements. So I will write here AC, main or even microgrid. These are the four control elements: voltage, frequency, active and reactive power. Okay. These we need to control. And this was the topic, this was the content of this week. And what's the need of microgrid control? Why do we need to control microgrid? And there are several needs. First is to control these key elements. That is the voltage and frequency regulation, then active and reactive power control. We always want to maintain the voltage within a tight band and frequency also within a tight band to avoid any kind of instability. And then we also want to have a control over the active and reactive power, which are linked with these two variables, V and F. Then we also want seamless transition between different modes. We already have studied and we already discussed about different modes of microgrid operation. The microgrid can operate in three modes. We already discussed. First one is the grid connected mode. First one is the grid connected mode. Second mode is the islanded mode. And third one is the transition. when there is a transition from the grid connected to the islanded mode. These three modes, we need a seamless transition between the modes, and for that we need to have a islanding detection techniques. And we have already discussed different types of islanding detection techniques, active and passive. Here we have discussed active, passive, hybrid, as well as communication based. Okay, then control is also required for participation in the energy market because we want to have an optimal cost operation. We want to minimize the cost of operation. And for that, we would always want to participate. Sorry. If let's say the market is offering less price, lower price, than the operating cost of the generators within the microgrid, then the microgrid controller should be able to do that. It should be able to reduce the generation. Let's say market price. I am denoting the market price by PM. Okay, market price is less than the price of the microgrid generators. Okay, generators. Let's say operating cost. I would say market clearing price is less than operating cost of microgrid in generators. In that case, I want to let's say we want to reduce the generation from microgrid and import from the main grid at market price. At market price. And so we will make a profit of around operational microgrid minus into this PM. So this will be the profit of the microgrid. The operation. This much profit can be earned, or this much cost can be saved by microgrid. If participation in energy market is, if it is there in the control algorithm of market of the microgrid controller, then the operation will be more economical. That's another reason why we need to have microgrid control. And then we also need uninterrupted supply to critical loads. We don't want to shed these critical loads. Even in the case, let's say, uh, this this interruption in the supply will be there in the case of islanding, right? Interruption of supply will be there in the case of islanding. So if even if there is interruption of the supply, we want to curtail only the non-essential loads. We want to still serve the critical loads. Because there are constraints on the storage. In islanding operation, the storage would be working, right? Let's say in evening time when renewable is not there, only storage is there. So this is the time when, so this is the peak time. Here storage, solar is during this daytime. Let me change the color of this. Okay, so this is the solar time. Now this is the peak time, and here solar energy is not available, but battery has already charged using that during the daytime. Now the battery can discharge here. Okay, but battery, if battery discharges more than 10%, below 10%, if the charge goes below 10%, then it is not good for the health of the battery. It will reduce its life cycle. That's why we want to avoid this kind of operation. In that case, we'll have to curtail the load. But we'll curtail the load which are not required, which are not that critical. We need the microgrid controller should have this inbuilt within its control scheme that the critical loads need to be served at any cost. Unless it's an very emergency situation where the battery is also fully discharged and there is no power. That's a different case. But the microgrid would be designed in such a way that it will be able to operate the critical loads always. That's the planning part of the microgrid. So before the operation comes the planning part where the microgrid is always, it will be planned in such a way that the critical loads will always be, will, the microgrid will always be able to supply the critical loads using the energy storage during the peak hours when the renewables are not available. So that's the planning aspect. In operation, if the planning is done very meticulously, then the operational, during operation, the control scheme will have to take care of this that the critical loads are served without fail. And then it can help in black start capability also. Say there is a blackout and the main grid needs support from the microgrid, then microgrid the energy storage. The energy stored in the energy storage can, it can support the main grid by providing that stored energy to restore to start the restoration process. Then optimized cost of operation is, it will happen when you participate in the market. And otherwise also among the available resources, it will try to optimize the cost of operation by avoiding diesel generators and such things. So that also it will take care. That's a very important aspect of the control of microgrid. And so many things we need to achieve. That's why the microgrid controller has to be very robust. Its design has to be very robust and its operation should be seamless. So then we started with the main topic was the hierarchical control. We need a hierarchical control. Single control or centralized control is not sufficient. Because the disadvantage with the centralized control is that if the link between that central controller and any one of the generator goes out, then we'll not be able to control. We need to have the observability from each and every generator in that case. And in central lights control, that's the main disadvantage. Although it's simple and it is easy to get an optimal solution in that case to achieve the global optimal, because the centralized controller knows each and the information of each and every element in the system. However, if any of the link fails, then then the control fails. In distribution system, so here we have a distribution network and then we also have a distribution network operator which has access to this distribution network and each of these microgrids, and the distribution network operator using the global control. So global control is there with the distribution network, and with that global control, it can interact with all the microgrid controllers. So each of these microgrid controller will be in each of the microgrids there is a microgrid controller, and this microgrid controller is the interface between the microgrid and the DNO, the distribution network operator. So DNO or the distribution management system has a very key responsibility here, and its responsibility is to manage the medium voltage and the low voltage areas in which more than one microgrid exists. So each of these microgrid has a layer of controls. Starting from the bottom, there is a local control, above which there is a secondary control, and the topmost is the central and emergency control. And then out of the microgrid, outside the microgrid, the control is the global control. So for each microgrid, there is one microgrid controller, which is MGCC, and that interfaces between the distribution management system and the microgrid. Distribution management system or the distribution network operator. Its main aim is to ensure that the distribution network is being utilized properly and it is congestion free, and the key control variables for the network at each bus and the frequency for the entire network voltage at each of the nodes of the bus, the network is within the limits, within the band. So that is the responsibility of the distribution network operator. Now we will see that these different controls one by one. Yeah, same thing is written here. DMS DNO has a responsibility to manage the operation of medium voltage and low voltage areas in which more than one microgrid exists. And this microgrid control center interfaces between DNO and microgrid. Now this again same thing, we can see these are the different uh, now first thing is we have seen here that these are the different layers of control: local control, secondary control, and central and emergency control, and above it is the global control. So this will local is the fastest, then it is slower, then this is slowest. As you move up, the time of operation increases. Local control has to be very fast. Now, each of these control can be decentralized, can be of three types. It, it can be centralized, decentralized, or distributed. Now we have seen, so there are four types of control: local, secondary, central, and global. So global is always a centralized control, and local can be decentralized. Local is always decentralized. Sorry. So it is clear that local is always, it is always a decentralized control. It is specific to that particular generator or distributed generator. Then global is always a centralized control, always, because its aim is to control the key variable throughout the network. And for that, it needs the information of each and every element, each and every microgrid in this case. And here the secondary and central, this can have, this can be distributed or centralized. Let's say in one microgrid, this is one microgrid. Okay, this is one microgrid, and it's connected to the other microgrids also, and to the main grid also. And here We have different feeders. It's going on. It's like this. And there are different sources here. So this is storage. Here we have PV. We can have wind farm here. And other sources are also there. Now we have different types of generators or DGs here, right? DG1, DG2. This is also DG4 and 5. Now each of these distributed generator will be having its own local control, which will be specific to it, which will try to regulate its voltage. And if it is operating in constant power mode, then to inject a particular amount of power, or to inject the maximum, or to extract out the maximum power from this at the particular voltage level. And so that is the work of local controller. And the effect of these individual local control will be there on the entire this microgrid. And that will have a particular voltage level here, and also trying to have a frequency, influence on frequency, or difference in the active and this load and generation mismatch or balance, which will affect that balance also. So in that case, we need a secondary control. And that secondary control will control all these distributed generators. Okay. Secondary as well as the central control will control all these generators. Now these generators can be controlled in a centralized fashion or in a decentralized fashion, or not decentralized, or distributed fashion. And that we will see. Whatever control we have achieved using the local control, if it is not able to bring the voltage and frequency within the limit, then the secondary and central control they pitch in. So this is the difference is shown here between the centralized control, distributed and decentralized control. In centralized control, we can see there is a central controller which have information about each and every DG, and it is having communication link with each of the distributed generator. If any of these link goes out, then this control will be affected. This control will not be foolproof. On the other hand, so this is one extreme. This is simple, but not reliable. Also, it is able to achieve a global optimum because it has information about the entire system. This is decentralized. Here it is reliable. It's very reliable. We can have the control here. You can say this is even more reliable. Here, if we lose one of the channels, still we can control, because these two are connected and they share the information with each other, and this information between these two is shared, and this two is also shared. In a way, the information about each of these entities is known. That's where distributed control. The problem here is more communication. The communication requirement is more extensive, and that's the main challenge here. And the global will always be centralized, local is always decentralized, and between that, secondary and control can be distributed and and centralized, distributed or centralized. In distributed, there are these three types of control schemes. Multi-agent system, we call it mass multi-agent system. Then this is model predictive control using some optimization. We try to achieve an objective function subject to certain constraints. And then this is a consensus algorithm. These are three distributed techniques. And this is the difference between all the control levels which we have already discussed. Here the local control, you see, it maintains. It is always decentralized. We already discussed this. Whereas global is always centralized. And central and secondary can be centralized or distributed. Here the aim is it maintains a DG stability by measuring and controlling local signals. Local signals. It controls the DGs to operate in normal operation. And the central control comes into picture when there is some emergency. It is important in islanded operation. The secondary is it ensures power sharing for parallel configuration of DGs. It compensates for voltage and frequency deviations because this will try to just inject its own power into the microgrid. But since each of the elements is trying to inject a particular power, that doesn't ensure that voltage will be within the limit. And this secondary control ensures that the voltage and frequency deviations caused by load variation and local control operation is minimized. And it improves the power quality as well as system performance. Then the central control is important in islanded operation mode. This determines the mode of operation, islanding detection, connection disconnection to and from the main grid, emergency control and overall protection scheme are part of this central control. So this is that microgrid central controller MGCC. And this MGCC interacts with the DNO through the global control. And this MGCC will be responsible for this islanding detection, this connection disconnection from to and from the main grid, and this entire protection scheme which we have discussed, the challenges faced by the DGs, the challenges for the protection scheme in the presence of DGs. That protection, the adaptive protection schemes, all those things are taken care by the MGCC. Then finally, the global control, it manages the power flow between the given microgrid, other microgrid, and the main grid. So these three pertains to a particular microgrid, and this will have control of power between different microgrids and between different microgrids and the main grid. And this control is outside the microgrid and within the distribution network. So it will take care of the distribution network between the microgrid. And it also ensures the economical optimal operation. It receives power references from the distribution management system and it is always centralized. That's very important. So the different types of, now we move on to the DC microgrid control. We have discussed the AC microgrid control. In the DC microgrid control, also we have three types of control strategies: decentralized, distributed, and centralized. In decentralized control, there are these different schemes: loop control, voltage leveling, DC bus signaling, and power line signaling. And in distributed, also we have this digital average current sharing, average voltage sharing with pilot bus regulation, distributed cooperative control, and then finally centralized control. The conventional droop curve which we use, right, for frequency, power, FV, and VQ, that are not applicable here for DC microgrid because in DC microgrid there is no frequency and reactive power. For DC microgrid, the control, the droop is between the V and P, the voltage and power. Here the droop changes. It is between the VDC and the power. The VDC and equals to VDC star reference of each converter. VDC is the output of, this is the output of converter. This is the converter output. And there's the reference DC bus voltage. And this is the output current and the virtual resistance. This is the droop, because we cannot have these two droop in DC. So for DC, the DC microgrid, the droop, we take the droop between VDC and the power output of that converter. And based upon that, we can have different types of droop control also. But the drawback for with the conventional droop control is that it degrades the current sharing accuracy due to unequal voltage drop across the line, and also results in poor regulation. Let's say one microgrid has a droop like this, and another DG has a droop like this. Now for the same level of, let's say this is power here. And this is voltage here. So for same power drop here, you can see the voltage deviation is this much, and for this it is only this much. And there is a very large difference. Similarly, it happens with the current also, and vice versa also. You can see for the same voltage. So for the same voltage level also, you can see same voltage level, the power sharing between the two is also very different. There is poor load sharing. There is poor load sharing when there is good voltage regulation, and poor voltage regulation for good load sharing. And also for a small group, there is less voltage deviation between the converters, but to the large difference. But for large group, there is a larger, but leads to larger difference in current sharing. Let's say these are the two grids with droop. It's very small droop. So for small droop, okay, the difference in current is so large. But when droop is more, it's the same for larger droops. The difference in current will be very small. This one, very small. This is I and this is B. So this is a drawback of convention. That's why there there are many methods which change the resistance. The advanced droop control techniques are used for that. Virtual resistance based, adaptive droop control, intelligence technique based, and more adaptive droop control. All these things are used. Different techniques have been used to overcome the drawbacks of this group control. Overcome the drawbacks of conventional group control. Now we move on to the distributed. The next type, the type of microgrid operation. So depending upon in in distributed control in digital average current sharing, so it says approach for an accurate voltage regulation and a load sharing. And it uses communication between digital average current sharing. What it does it in the conventional Droop equation which is there, it adds one more component. We have seen VDC and is equals to VDC star minus IDC and RDC. It adds one more element here, delta VK0 here. And this delta VK0 is equals to GK IK average. That's why name is average current sharing and IK rated. And this IK average is equals to IJ per unit divided by N over J. Okay. It will take the average current. It adds this term and it improves the voltage regulation and the load sharing. This is a simple concept of digital average current sharing. Then average voltage sharing with pilot bus regulation. And then last one is a distributed cooperative control. It uses multi-agent system. And this is generally employed where we have heterogeneous storage. So different types of storage. Battery, supercapacitor. In this case, it is used and to ensure that the storage device does not have energy deficit in it at any point of time. So next is the types of DC microgrid operations. So here we have two. We've already seen in the previous sessions also that microgrid can operate in three modes. Any microgrid can operate in three modes: grid connected, islanded, and in transition. Yes, and there is a transition from grid connected to islanding mode or islanded mode to the grid connection mode. That is also called as a restoration phase or mode. In this case, we're discussing here about two, and the third one will be the transition phase that we will discuss in the AC/DC hybrid microgrid. So here, these are the two modes. One is grid connected and islanded. And in islanded, there are two cases. One is when there is only a single microgrid. Other is there are different microgrids, multi-microgrids. In this single microgrid case, the decentralized scheme, we have seen that there are three types of control schemes. One is centralized, one is decentralized, and another one is the distributed. Centralized and decentralized are the two extreme, and the distributed combines the advantages of each of these to give a more reliable and yes, more reliable solution control algorithm. The decentralized is more reliable and cost effective here. And in this case, what will happen? In this case, the distributed generators, because it's an islanded mode. Now there are two cases. Either there is surplus generation or there is the load is more than the generation. First is either generation is more than the load or load is more than the generation. Here, if the generation is more than the load, then the distributed generators, and this decides the operation of these operational modes of different distributed generators, as well as the energy storage. If generation is more than the load, then the distributed generators, PV, wind, they will operate at the MPPT, at their MPPT. MPPT means maximum power point tracking. So they will be operating in such a way that the maximum power is extracted from PV or wind for the given insolation or the wind speed by varying the voltage in case of solar PV and by varying the pitch angle in case of the wind. Okay, yes. So they will operate at maximum power point, and because generation is more than the load, the excess generation will be stored in the energy storage. And if the energy, so excess, they will operate in MPPT. Here also we can have different cases. First is they're operating in MPPT and plus they are charging the battery energy storage, but it is charged. It is its SOC is less than 90% or zero point 0.9. Second is DG, although generation is more than the load, but they cannot operate at, or let's say off MPPT. They cannot operate at MPPT because energy, the SOC of energy storage is already more than 90%. It is at 90%, and we cannot charge the storage more than 90% or discharge it below 10% for its durability. If we overcharge or over discharge the battery, then its life will reduce, and that will increase to the cost of operation of the microgrid. We don't want that. So in this case, when generation is more than the load, then distributed generators can operate at MPPT also, and also may not operate at MPPT. That will be determined by the storage, the charge in the storage. If charge is if it has already reached 90%, then they cannot operate at their maximum power point. But if the charge is SOC is less than 90%, they can operate at their maximum power point and charge the battery as well as provide the supply the load. The second case is when the load is greater than generation. So in this case, they will be operating at maximum power point and supply the load. Because they are operating maximum power point, they will supply the load. So in this, therefore, whenever they operate at maximum power point, the storage will regulate the DC voltage, DC grid voltage. Because in this case, load is greater than generation and they will operate at maximum power point. Even after that, they are not able to meet the load. Therefore, storage will discharge. energy storage will discharge here. It will discharge only up to 10% of SOC, its rated capacity. Beyond that, it will not discharge. So as the SOC starts reducing below a certain point, we need to curtail the load to maintain the generation and load balance. The loads are curtailed based upon the priority of the load. Those which are non-essential loads, they will be curtailed first. And the critical loads we cannot curtail them because that's the part of planning of microgrid. So we are discussing here the operation of microgrid, but before starting the operating a microgrid, first step is to plan the microgrid. The microgrid will be planned in such a way that renewable, even if in the islanded mode, during evening time when the renewable is not available, even at that time, at least the critical loads must be satisfied or served by all the generations combined with the energy storage. That planning is done beforehand. And while operation, we need to ensure that this happens in the most cost-effective manner. Okay, so this was the case of the single microgrid. Now, in the case of multiple microgrid or multi-microgrid, different microgrids they can combine together to form a cluster, and they can share power in between them. And in this is the case where, let's say, here single microgrid can have the deficit of generation, but in multi microgrid, let's say there are two microgrids, MG1 and MG2. Let's say MG1 is having load less than generation and MG2 load 2 amps. Here load 2 is more than generation in the microgrid 2. Then what can be done? The power can be exchanged between these two microgrid. The microgrid 1 can supply excess power to microgrid 2. They can exchange power. In that case, they, there is an overall improvement in the reliability as well as better utilization and suppressed aging and stress of component. This will, if stress of component reduces, then the maintenance cost also reduces. And overall, the lifespan of the product on the component will increase. In multi-microgrid, there are two modes. One is autonomous mode and one is connected mode. So in autonomous mode, each microgrid has its own control layer to support its local load. Whatever benefit which are written here, it can be obtained when the multi-microgrids operate in the connected mode. Then in that case, power flow among microgrids may be controlled to optimize the utilization of their energy sources. And this can be achieved by regulating their bus voltages. The, the microgrid with the higher voltage transfer will supply power to the microgrid with the lower voltage. That voltage difference will help in the power flow, in controlling the power flow among the microgrids. So this was the DC microgrid. Then why do we need the AC-DC hybrid microgrid? Can you tell why we need hybrid microgrid? Okay. The existing grid is AC grid. Existing or conventional grid, or we can say the main grid. Conventional main grid. It's an AC grid. But we have sources which are DC as well as AC. In DC, we have solar PV, we have fuel cells, we have batteries, electric vehicles. uh, They can act both as source and load. And then supercapacitors. Okay. Similarly, we have loads also, both AC as well as DC. These electronic equipments, they're all DC. Internally, they work on DC. Externally, we need to convert the AC into DC because the main grid is AC. If sources are DC, loads are also DC, why not supply the DC load directly from the DC sources? And because if we do that, we can save on efficiency. We can make the system more efficient because we save the conversion. We avoid these conversion stages between. Use the PDF now. Let me just stop sharing. I will share again. I hope it's visible now. Okay. Yes. We were here by SCDC, hybrid microgrid. Okay. So we have AC loads, we have DC loads, we have DC source. Then why not use? Why to use that? We can directly. We have AC source, AC loads. We have DC source and DC loads. When if we can supply the DC loads directly by DC source, then we can avoid this DC to AC and AC to DC convergence. Right? Just sorry. So we can avoid these AC to so this AC to DC and then DC to AC conversion stages. So this will be required for AC loads, and this will be required for an AC source supplying the DC loads. So these stages I can avoid. So you can avoid this AC, DC, AC, and DC, AC, DC conversion stages. Because in the because existing grid is AC, we need to convert the solar PV which is in DC, and to supply DC again we need to convert the existing AC into DC. Similarly, here we convert AC into DC, then again DC into AC. Is there an example for this? AC to DC and DC to AC? Then say storage. If storage when it is charging from the AC grid, then we need to convert the AC into DC. Then when it is discharging again to the grid, then again we need to convert the DC into AC. But if storage is directly connected to the DC bus, DC microgrid, where it is being supplied by the PV source, and then it is directly supplying the DC loads, then this step can be avoided. So yes, so these are the three microgrids. First is AC, DC, then AC, DC microgrid. Here the main grid is AC. Here DC, it is here both AC and DC are there. Exchange of power is on AC platform, here on DC platform, and here on AC, DC. In AC grid, the common stages are AC, DC, AC. And in DC grid, AC to DC to AC. Here we took the example of energy storage. Right? And here you can see while using any electronic equipment, you can see. Because solar power is feeding to the AC grid, and which is then providing power to the electronic gadget. Then again AC to DC's conversion is required. Okay. So here the purpose of connection to the grid in all the three cases for all the three microgrid is to increase the reliability of the loads and to have power sharing. When there is excess power in the microgrid, it can deliver it to the supply it to the main grid. And when there is a deficit in microgrid, it can import power from the main grid. There are two structures for AC, DC hybrid microgrid. One is where the AC loads and AC source and DC loads, sorry, AC loads, AC source, DC load, DC source are there on both the sides, on AC side as well as on the DC side, which you can see here in the structure one. We have DC bus here, we have AC bus here, and this is the main grid. And on this DC bus, there are DC load as well as AC load. DC load can be directly fed, but for AC load, we need to convert DC into AC. Then we have both type of sources also, DC sources, AC sources. So if it is a DC distributed generation like solar, then directly using a boost converter, we can connect it to the DC bus. If it is AC distributed generation like wind, then we need to convert AC into DC and connect it to the DC bus. And storage element will require a bidirectional converter because it can both charge and discharge. And then on AC side also, if we see here, if we have AC distributed generation, then to make it variable, we need to have AC, DC, AC. For DC generation, DC into DC to AC conversion is required, and storage bidirectional. Here we can have both AC and DC load. DC load is also possible here. In that case, we will require a DC to AC conversion stage. Sorry, AC to DC. Okay. And these two buses are connected by these bidirectional interlinking converters. So this is the first structure where distributed generation storage elements and loads are present on both the buses, both DC and AC buses. This is preferred. Disadvantage we have already discussed the last in previous slide with the disadvantage which we discussed for they pertain to this particular structure only. The disadvantage is this DC is you can say AC DC AC here DC AC DC. These stages they reduce the efficiency. AC DC AC. Here you can say DC AC DC AC. These stages are there which reduce the efficiency, overall efficiency of the system. So these are preferred when major power system are both AC and DC. Now structure 2 is very convenient, but it is difficult to plan in such a way. But if we can plan, then it's very wonderful. We can save a lot on efficiency front, but it's difficult to plan because for that we need to have all the AC sources and all the AC loads only on the AC side, and all the DC sources and DC loads on the DC side. And in between, they will be linked by the bidirectional DC-DC, DC-AC converter or AC-DC converter. If this is AC microgrid, then it is DC-AC, bidirectional DC-AC converter. On AC side, we have wind. It is connected to the main grid, and we have diesel generator and AC loads. On DC side, PV array, battery is there, super capacitor or ultra capacitor, and DC loads are there. Fuel cell can also be there on the DC side. These are the two structures. So here we are able to avoid these conversion stages, and that's why it improves the efficiency and it also reduces the system cost. Okay. Now, next part is the different management. So we have already discussed the control strategies in AC and DC microgrid. Now the same we discuss here for the AC DC hybrid microgrid also. So any kind of microgrid, whether it is DC, AC or AC-DC hybrid microgrid can operate in grid connected mode, islanded mode and the transition mode. This grid connected mode, it can have two modes. One is dispatched power modes and another is the undispatched power mode. Dispatched power mode means we can schedule, we can decide how much the DC will generate. That's why economic dispatch we use for conventional generators, right? We dispatch the generators to minimize the cost. Here we in economic dispatch we want to minimize the cost of operation of generators. Here it is over G, subject to the summation of generation is equal to summation of load. And this is for thermal generators. And then if we solve this problem for certain number of generators, we find out how much each generator should generate. They also have some technical constraints that PG should be between PG max and PG min. Considering all these constraints, we can know how much each generator should generate, and it is dictated by its by the cost of these operational cost of these generators. In dispatch mode, we can have control over the amount of power which the microgrid will supply to the main grid. But it can also absorb power from the main grid. And we are doing this in order to benefit the main grid, to provide some services to the main grid. Same thing is written here. To grid support services. In this mode, we can provide the grid support services. The microgrid can provide support services to the main grid by controlling the active and reactive power delivered into the grid. So here the microgrid behaves like a controllable source or load to the main grid. Now if it is having excess generation during daytime when solar is at its peak, in that case it will act as the microgrid will act as a source of power, and it will supply inject P and Q into the main grid, and it can help improve the voltage profile of the main grid. Okay, or even restore the frequency to its nominal value if it was less before. And similarly, it can also reduce its generation. Let's say the PV, there was in daytime, PV was at its peak and battery is fully charged, load are already met. In that case, the microgrid can provide more power. It can sell the maximum. It can export power to the main grid because there is excess generation in the grid, but there is already over voltage on the main grid side. Then in that case, it will not operate on the maximum power point. It will operate in off MPPT mode or voltage control mode and reduce its generation in that case to help the main grid. So here the dispatch power is shared. But this dispatch power, how much power is to be dispatched will be decided by the microgrid control center, the MGCC, the central control of the microgrid, and it will share that power among these different power sources present within the microgrid. And in the so here in dispatch power mode, there are two modes. One is current control mode and one is the voltage control mode. Here in current control mode, the current is controlled to track the reference power and the voltage and frequency are determined by the grid. So this is the case when the microgrid is supplying power, injecting power into the grid. It's only possible in the grid connected mode. It will be controlled to track the reference power. And then in the voltage control mode, they cannot operate in MPPT. They will have to control the voltage like a synchronous generator. And then this can be used in both grid connected as well as islanded mode. Islanded mode also, some of the at least one of the DG has to operate in the voltage control mode because the voltage reference is not available from the main grid. We have seen the grid forming grid that grid supporting, grid farming, and one more is which one? Grid feeding converters in the previous week. In the grid feeding, in grid, when the microgrid is in islanded mode, we need at least one of the DGs to operate in the grid farming mode. Others can operate in the grid feeding mode. So that will be the voltage control mode, grid farming. Okay, so then this is the dispatched power mode, and in undispatched power mode, all the generators. Here we are not deciding which generator is going to produce how much. All the generators here will be operating at their maximum power point, and they will be feeding the excess power into the grid. Whatever power is there, entire excess power they will be directly feeding into the grid. So here that's why all the generator, wind, solar, they will be operating in the maximum power point at their MPPT point. And the storage elements here, because they are generating maximum power and it's even more than the load, then the storage will be charged up to 90%. And beyond that also, if there is excess generation, that excess generation will be sent into the grid. Okay, this is again, this is how in these different modes, different elements operate. It's again more detailed version of the previous slide. Here, same thing we are discussing here, but again discussing that whatever we have seen here, we have different types of components in ECDC microgrid. One is we have these distributed generators, DGs, and then storage element is there, DGs, storage elements, and then interlinking converters are there. And how these three will operate in which mode, that is discussed in this slide. In each of the mode of the AC/DC hybrid microgrid. In the grid connected mode, we already seen there are two modes. One is undispatched and one is dispatched mode. In dispatched mode also there can be two options. First is that the interlinking capacitor that operate in the DC bus voltage control mode. That means it will control the voltage of the DC bus, because here in AC/DC hybrid microgrid we have two buses, AC bus, DC bus. For AC bus we need to control voltage and frequency. For DC bus we need to control the voltage. So in dispatch mode, the interlinking capacitor will work. Sorry, converter will operate in a DC bus voltage control mode. And while these different distributed generators on AC and DC side, they will coordinate with each other to ensure a power balancing. Because in dispatch mode, what we are doing, we are either supplying power to the main grid or absorbing power from the main grid. So in that case, to achieve a particular goal, what type of support we want to provide to the main grid, that will be decided or communicated by the microgrid control center to each of the DGs. And then those DGs will have to, because that control center will generate a reference for these DGs. And these DGs will have to track that reference. And to ensure that global, to let's say to inject a particular amount of power or to absorb a particular amount of power, this DG will share power between these two sides, AC and DC sides, to ensure the power balance. They are not trying to maintain voltage at their terminal. In this case, they are trying to track the P and Q reference. And that's why the maintaining the voltage at the AC bus as well as the DC bus, that will be, so the DC bus will be done by the interlinking capacitor converter. So interlinking converter will try to maintain the DC bus voltage in this in this mode. Yeah, that is one strategy. So second strategy is that the DGs and storage element on the DC side, they control the DC link voltage, the voltage at this DC bus. So they try to maintain a fixed voltage level at this bus, and the is interlinking converter and the is distributed generators and storage on the AC side. They work on the power control mode. They will inject a particular amount of power. So because power is related to frequency, so if they inject a particular amount of power, the frequency will also be taken care of. Okay. So this is dispatched. Then in undispatched, because here they will be operating at maximum power point. In this, we can see DGs both on AC and DC side, they will operate on maximum power point. And the storage, because they are operating at maximum power point, either they will charge if their SOC is less than 90%, or they may discharge for smoothing out the output for helping the grid. And the interlinking converter, it will try to maintain the voltage because these distributed generators and storage are already operating in a power control mode or MPPT mode. So they cannot help in voltage control. That's why the interlinking converter will try to maintain the voltage at the DC bus and inject all the power generated by the distributed generators into the main grid. This was the grid connected mode. The next is this standalone mode. And here in standalone mode, because the microgrid is now it's no more connected to the main grid. It's why maintaining the voltage and frequency simultaneously. The voltage maintaining voltage simultaneously on AC and DC buses is important here. And the DGs need to take care of that because there is no external grid here, no reference also. So one of the DGs will have to provide a reference voltage also. That's why in this case, the depending upon the mode of operation, the interlinking converter can work either on AC link voltage control, DC link voltage control mode, or output power control mode. So here that in DC bus, the DC link voltage can be controlled either directly or indirectly. So directly is by using droop control. In AC we have seen droop is PF or QB. These are the droop characteristics which we use in AC microgrid. But in DC microgrid, these droops are not available because frequency is not there. In DC, frequency is zero, and so there is no reactive power also. These droop are not applicable for DC. In DC microgrid, we have droop between VDC, the DC link voltage, and the output of the distributed generator peak. This droop is used, and that is a droop control here. So that is a direct control of DC link voltage by using the droop control, and indirect is by having the power balance between the demand and generation. So DC link voltage control can be achieved by using direct or indirect control. Okay. So the previous slide was on how to control the Microgrid in grid connected and standalone mode. Now this one is the third mode. How to control the AC/DC hybrid microgrid when there is a transition from standalone to grid connected or grid connected to standalone. That's why it is power management strategies during transient and loading condition when the load changes and how things will how to change. Things will have to be changed here. Okay. These power management strategies. First, for both of these, for transient and loading conditions. First, we are seeing for transient condition. In transient, there are two types of transition. One is from grid connected to standalone, and second one is from standalone to grid connected mode. So this is also the restoration. The restoration of the main grid. The microgrid is being connected to the main grid. And this is the grid connected to standalone mode, which is the islanding. Grid connected to islanding mode. Okay, so here we need to know the islanding. We need to detect the islanding, the event of islanding. So islanding detection techniques are required, which we have already seen in week 5. In different types of islanding detection techniques, active, passive, and hybrid, active, passive, islanding detection techniques, and last one was communication based. Hmm. These are the different islanding detection techniques. Because based upon the detection, once the controller knows that there is an islanding event, that there is a transition from grid connected to standalone mode at a particular time in event. And in that case, the control needs to change. Initially, the DGs were operating in the current control mode. Now they need to shift to the voltage control mode because there is no more voltage and frequency reference from the main grid. Or we can say if all the DGs were operating uh, in the grid feeding mode, now after transition to the standalone mode, at least one of them needs to operate in grid farming and others can operate in grid feeding. So that one particular DG yes. Yes, so that one particular DG which we want to operate in, we want to change its operation from grid feeding to grid farming. And we have seen that how can we model these grid feeding and grid farming. It's a voltage source in series with a small impedance. And this is a current source in parallel with the large impedance Z. So that's why I say earlier it was operating in current control mode. Now it will be operating in the voltage control mode. And this one particular DG has to take this responsibility. At least one. More DGs can also operate in the grid farming mode, but at least one of them has to operate in the grid farming mode. And that DG has to switch from grid feeding to grid farming. And for that switching, the microgrid controller needs to know that the switching is required. control switching is required, and for that islanding detection is very important. That's why here we need to know the islanding, we need to detect the islanding event. This is one strategy, I would say this first. And this is a second strategy where the control scheme can be such that no need to change, switch from this current control to voltage control and voltage control back to current control. It is what we can say transition agnostic. That's why it is called uniform control. Uniform means it's same throughout. It doesn't. It doesn't. It is not affected by the mode of operation. It, it's agnostic of mode of operation. Mode of operation agnostic. That's why it's a uniform control. The control is same throughout. It need not change. So these are the two strategies which are required. And in second stage, because the mode of operation doesn't matter, the islanding is not required as such, but to have a uniform operation and to meet the requirement of the standards, it can be there. But in practice, it's not required. Okay, to improve the performance, islanding is there, detection is there. And then there is in transition, there is also power sharing among the distributed generators. So these are the two main strategy here in the grid connected to standalone mode. And then when we move to standalone to grid connected mode, that is a restoration process. Here first first step is to synchronize with the grid. We cannot directly connect the microgrid to the main grid because microgrid is operating at a particular voltage level and a frequency. And we cannot directly connect a system at a particular voltage level directly to another system operating at a different voltage level. If you want to connect two AC system operating at two different voltage levels or two equipments operating at two different voltage level you want to connect, then the voltage difference, the voltage between them should be very small, both magnitude as well as the phase angle. And that is called as synchronization. And that synchronization can be of two types. One is passive and another one is the active. So in passive, it is assumed. So in passive, simply we keep on monitoring the voltage of the microgrid as well as the voltage of the main grid. And whenever those two, the phase difference and magnitude between the two is very small, we simply connect it. Here it assumes that the voltage is very close and frequency differs very slightly. And this technique is not a fast technique and it is not that seamless also. There will be transients in this case. So here we cannot guarantee fast and controllable synchronization. And in this case, there is no detection. Islanding detection is not required here. We can simply monitor the magnitude and phase angle of the voltage of the microgrid and main grid and simply connect it. But the disadvantage here is the transients are there. We cannot completely avoid them. But in active synchronization, we can do that. We can avoid those transients and we can have a very quick and a seamless transition from standalone to grid connected mode. And for this, here also these are two different methods. One is here one not all the DGs participate in synchronization. Few DGs initiate and then other follows. So microgrid with some DGs in current control mode. And here, because the remaining Here, what is the same thing which we already discussed, that in islanding mode, how many converters are operating in grid farming and grid feeding. That is also a big research. It's a research problem. How to decide? How microgrid is going to decide? The microgrid controller is going to decide that how many converters or the distributed generators should operate in the grid farming or grid feeding mode. If all of them operate in the grid farming mode, then all the DGs they participate in the active synchronization and they all will operate in the voltage control mode. But if only few are operating in the grid farming mode, then only they will participate in the synchronization. Other will be operating in the current control mode. And then they will switch and to voltage control mode. So in this case, communication is a very important thing. Here, communication is required between the main grid and the microgrid. To control the microgrid control center has to have a good communication with the distributed generators here. Now here you can see here standalone to in grid connected to standalone, there is a change in control scheme and voltage synchronization before reconnection. Here in standalone to grid connected. In grid connected to standalone, there is a change in control scheme. In loading condition, the constant power loads they can cause instability because of their negative impedance characteristics. And in standalone, voltage and frequency deviations are dependent on each other. The load's voltage and frequency, the dependence may cause instability. So the loading condition is also very important. Whenever the loading condition is changing, the controller should able to cope with that, should able to cater to the changes in the loading condition as well. So that is also very important. Let me share the PowerPoint again. I will stop sharing now and share again. I hope the PPT will work now. Yeah. Uh, so just a minute. Okay. Now I'm sharing the PPT. And find that. Yes. Yeah. I hope it's visible. Let me go to the full screen mode. Yes, perfect. We were at this point here. Yes, we were here. Here. So we were here in standalone to grid. We need to change the control scheme. and we need voltage synchronization before reconnection. There are there are two methods. One is passive synchronization and one is active synchronization. In active synchronization, one or more DG initiate and other follows. And here, the microgrid with some DGs operate in the current control mode. And then second is all DGs participate. Here, microgrid with DGs in voltage control and communication is essential here. Okay, let us now move to the questions today. Questions for today. That, so what first question is the key control variables in a DC microgrid. Remember, this is DC microgrid, not AC microgrid. We have discussed the key control variables for AC microgrid earlier. We had discussed for both AC and AC, and we discussed four key control variables which are there required for AC microgrid. What are those? Voltage, frequency, active power, and reactive power, right? P and Q. These are the four key control variables for. So these four are required for AC and for DC because frequency is not there and reactive power is not there. Frequency is not there, reactive power is not there. So V and F, these two are required for DC microgrid. Key control variables in DC microgrid are voltage and active power. Voltage and active power. So option B is correct here. This is fine. Okay, let us move ahead now. Next question is which of the following hierarchical control is correct from bottom to top? Okay, now we have discussed four types of control, right? Three are there within the microgrid and one is outside the microgrid. So which is outside microgrid is global control. And within the microgrid, we have on the top is central microgrid control center. The central control microgrid MGCC, that's central control, central or emergency control. Then we have secondary control and we have local control. They're also called as primary, secondary, and tertiary control. These three are within the microgrid, and fourth is a global control. This is bottom to top. The bottommost control is the local control, which is for a particular DG and which is always decentralized. So I am repeating again and again so that you can remember these things. Never forget. And this is always centralized. And these two can be both. These can be either centralized or distributed. These can be centralized or distributed. Okay. So in distributed, we have seen model predictive control, agent system mass, and consensus algorithm. Okay. Which of the following is true? So what was the answer? Yeah. So C is the answer. Local, secondary, central emergency, and global. Next question is which of the following is true in case of conventional group control in a DC microgrid? So conventional group control, first we have already seen that in AC, group is different, group characteristic characteristic for DC and AC are different. For AC, there is the droop is between PS and VQ. For DC, it is between VDC and P. So which of the following is true in case of conventional droop characteristics? The reference DC bus voltage remains constant throughout. Reference DC bus voltage increases with increase in output current. And the reference DC bus voltage is reduced with increase in output current. Last is reference DC bus voltage decreases exponentially. So exponentially is not possible because there is a linear relationship between current and voltage, right? This is a linear relationship. This is not correct. This is also not correct. Reference DC bus voltage. If it remains constant, how are we going to control it? There is no question of control. So this is also not correct. Now, if the current, let's say, if current increases, then what will happen to the voltage, to the DC bus voltage? It will reduce. If the reference DC bus voltage is increased, if the reference DC bus voltage remains, so reference DC bus voltage remains same, but the this value will change. If it is same, if current increases, then this will reduce. Output voltage will reduce. The reference DC bus voltage will remain constant throughout. Which of the following decentralized control is limited to very small renewable energy system? It is the which one? Voltage leveling, because it's that voltage window depends upon the number of DGs connected. Next is in the hybrid storage system, which of the following device help to compensate for higher frequency switching transient? So this also let us again revisit this point. So we have hybrid energy storage systems. Hybrid means we are using two types of system, two energy storage systems here. We are exploiting two different properties of these two energy storage. First type of storage is high energy density. High energy density, these are relative to each other. If this is higher, means one is higher than the another. Higher energy density and low power density. Second one is having comparatively a lower energy density and high power density. Okay. So battery energy storage is a high energy density device as compared to the supercapacitor, which is a high power density device with respect to this battery. It can provide quick charge discharging, charging and discharging. That's why it can be used to compensate high frequency switching transient. While the longer discharge duration uh, requirement can be met by the battery energy storage. So here the answer will be supercapacitor. Okay. Next question is the modern electronic loads when they are connected to the isolated AC microgrid having PV as a single source of energy. So loads are the modern electronic loads. Which require DC supply. And the source is, first of all, the microgrid is AC. So it's an isolated AC microgrid, islanded AC microgrid. And the source here is DC. And this, because it's an AC microgrid, the power supply is, or platform is AC. So load and source both are connected to the AC bus. The source is DC and it is connected to AC. It will be connected via AC-DC converter. And then because load is DC and we need to convert that AC into DC. So what is the conversion stage here? DC, AC, DC. Correct? Okay, same question now in a different way. Similar question, not same. When a motor load is connected to isolated DC microgrid, it's a DC microgrid, first of all, isolated DC microgrid. That means we have DC bus here. The source here is AC, which is wind, and then motor is AC here, AC motor load, AC motor load. The load here is a AC motor, and in between we have a DC bus. This is AC motor connected to a DC bus. It will be connected via AC-DC converter. And the source is AC, and because it is connected to DC bus, it will be connected via AC-DC converter. AC-DC. What is the loss? Conversion loss here. Conversion loss here is happening in AC, DC, AC stage, conversion stage. Opposite to the earlier one. The previous one was DC, AC, DC, and this is AC, DC, AC. Okay, next question. The role of interlinking converter, distributed generator, and storage elements, respectively, in the case of a grid connected undispatched power mode. So we have to see here. It is first of all grid connected and it is undispatched. That means they're not supposed to operate at a particular power point. That means they can operate at their maximum power point. So dispatched power mode of operation of AC/DC hybrid microgrid is. So what is the role of these different elements? So what is the role of DG here? The role of DG is to operate at maximum power point operates in MPPT. These two are not correct. Operates in MPPT, and storage element here can both charge and discharge, and ILC will regulate the DC bus. So in between these two operations, this is not correct because it cannot always charge. Because if the SOC, it can only charge when SOC is less than 90%. SME. But if once it reaches 90%, it will not charge. Therefore, it can charge or both discharge. This is the correct option. And since the DG is operating at maximum power point, it cannot regulate the voltage. Regulate the voltage regulation will be carried out by the interlinking converter. Which of the following type of load can cause instability issue under carrying loading condition in AC/DC habit microgrid? We already seen that's a constant power load here. Then next question is global hierarchical control is. We already seen global is always centralized, local is always decentralized, while secondary and central or emergency can be centralized or distributed. Centralized control. Poor voltage regulation in group control DC microgrid is due to this also we have seen. If there is small group and versus there is large group, in which case let's say this is P and this is B. In which case it's not, this is not correct. What to say? This is large group, this is small group. The small group will have poor regulation. Small or large? Large group quantities. Large group quantities will result in large voltage deviation or poor voltage regulation. That is correct. So this is Large droop will result in large voltage deviations. Large droop quantities will result in poor voltage regulation. Which of the following entities is responsible to maintain the DC bus voltage in grid connected DC microgrid? DC bus voltage in DC in grid connected microgrid. Grid connected microgrid in DC bus voltage. DC microgrid. In DC microgrid, who will maintain the DC bus voltage? Voltage source converter interfacing DC bus to the utility. That is responsible to maintain the AC voltage. And next question, in islanded hybrid AC/DC microgrid. First of all, it is islanded. Second, it is hybrid. Has excess RE and fully charged ESS. Excess RE, fully charged ESS. That means it is operating at MPPT. Excess fully charged ESS. Uncontrolled load both in AC and DC. Possible solution to maintain the system is excess generation, then is operating the renewable in. We cannot charge, load shedding is not required, only generation is more. So operating renewable in power dispatch. That means to fix the power to its maximum. Fix the power to the value which is required to meet the load. That is sufficient. Okay. Next is, my laptop is already was about to discharge. So this is the last question, then we will stop. Select the correct statement regarding PMSG in a DC microgrid. Variable wind speed is first fed to uncontrolled rectifier. PMSG is AC. It will go to uncontrolled rectifier, variable DC. Then DC boost, which will have MPPT, and wind curtailment is achieved by using pitch control. That is correct. So all these three statements are correct here. Okay. So let us stop here. Thank you very much for joining the session today. And we will meet next Monday, same time from 6 to 8.